Good morning. I hope you all are doing well. Happy Friday. Happy last day of the term. Before we get into Chem 223 stuff, this is Dr. Elizabeth Cohen, and she wants to talk a little bit about organic chemistry.
Do you normally have more than this?
They'll start showing up here.
Oh, okay. So, as you might know, we offer organic here. We're one of the community colleges. They don't all offer organic, but we offer all three terms of organic. And yes, the rumors may be false that it does transfer. It does indeed transfer. It is not a big deal to get it to transfer. You might hear people tell you, oh, but you have to take a special test to get it to transfer. This is not true. The way it works here when you take it at the community college is if you take all three terms and you pass this ACS final with a 50th percentile or above, you get upper division credit, meaning you get junior, senior level credit for it, as if it were a 300 level class. Because normally we're not allowed to offer 300 level classes at a community college. If you do not get a 50th percentile or above, it still transfers, just not as a 300 level class. So you still, regardless, always get credit for organic chemistry. And that whole thing about transferring is just our universities and Oregon's issue. If you wanted to transfer this outside of Oregon, or you wanted to go to a private college, they don't care about the ACS exam. I think it's because they're worried about the money here. And that's why they don't want you to take it here. But you get a much better education in organic chemistry by taking it here because you see me all the time, as opposed to a grad student who may or may not speak English very well and may or may not know their material very well. You're also in a class of 300, maybe more. Did they ever ask you questions?
Once in a while.
Once in a while. Do you think they would ask questions in a class of 300?
Probably.
No. No, you went to a large university. You know how it works. So you don't get the personal touch if you leave, if you go to a big class. But here you get the personal touch. In terms of my record of passing the ACS final, every single year I've definitely had 75% or more pass it. There was one year I had, we'll count it as 100% pass it, because the one person who didn't, did it incomplete. And when you take your ACS final a year later, you kind of get the idea, it's not going to be so hot. Unfortunately, he was an A student who did the incomplete. So that was a little bit sad for me. But it's a good class to take here. It's a much more pleasant experience. No matter where you take it, it is going to be a killer class. So putting it off isn't going to help you. The other thing is, if you wait to take it, if you're going to move to the university, say not next year but the year after, you're going to have to be at the university for 3 years because you're now behind schedule. At the university, people take it sophomore year. Yeah, it's an upper division class, junior and senior, but you take it sophomore year. Yeah, that's, again, our university system stupidity of it all. If you went to another university outside of Oregon, it would be a 200 level class because you take it sophomore year. Questions about OChem? I know I talked fast because I know you want to take class. So if you have questions, you can email me and ask me about it. It is a small class. We generally start the fall with about 20. Right now I'm down to 12.
So with this ACS exam, is it like you take it like at the final term?
At the very end. So it's a cumulative exam just like this one is. I actually give you a study guide for it, a book published by the ACS final, the ACS whatever company. And if you just do what I tell you to do and you practice that book, you will pass it with a 50th percentile or above. The only people who don't are the people who do not do what I tell them to do, which is to spend some time looking at that book.
Okay, so it'll be at the end of the third
term, yeah. So if you only need 2 terms because you're an engineering major, don't worry about it. It still transfers. It's just not called a 300 level class. And you just have to take another 300 level class for those upper division credits when you transfer. But you still get OChem credit. You don't have to repeat it when you leave. Other questions?
Thanks, Elizabeth.
Welcome.
Very cool. All right.
Have fun.
Will do. So back to our ACS exam. We are down to the final lecture. I am so excited to be here. For most of you, the only thing that I will see you for next week will be next Wednesday in this room at 8:45. It'll go 8:45 to 10:45. Those of you in the Wednesdays class, I do have the 110 to 310 part in 2501. But when you come to that, make sure you bring a calculator, pencil, Scantron, 100 questions total, and the final exam prep sheet. And that's really all that's left that's due and stuff for Chem 223, which is pretty exciting. Should have final grades up by Thursday. Any questions on this kind of stuff? Good luck. We're going to try and bust through a lot of questions today, so I might go a little bit faster and stuff. Again, I'm hoping that a lot of this is review, but just letting you know. All of the groups on the periodic table have a generic electron configuration. And see if you can figure out which one of these is for the alkali metals. So I'm basically asking you to figure out which one the alkali metals are, and then also what the generic representation would be. All right, good. All of you picked basically things corresponding to group 1A or group 2A. So group 1A, the little n right there, the n is the period number. So like hydrogen is 1s1, lithium would be 2s1, beryllium would be 2s2. So the n changes depending on which one you is. All of the group 1As will be ns1, and all of the group 2As will be ns2. So really the only question is which one is the alkali metals, and most of you saw, well done, that it's the first column. If you put the second column down, don't despair. The second column is the alkaline earth metals, which sound very close to alkali metals. Sorry about the confusion in the names, but the alkali metals would be group 1A. Which one of these would be a halogen? NS2 and P5. Good, that's right. The halogens, the halogens are group are the NS2 and P5. They would exclude the Ds, which is very common for them. Here's a bunch of elements. Which one of these has the largest atomic radius? This is a periodic trend, all right? See if you can figure out which one is the biggest. Have to pick something based on biggest or smallest. If it's a periodic trend, it's either going to be the one that's most left and down or the one that's most up and to the right. So of these four elements, the real one's not JQ. It's either going to be sodium, all right, or most up and to the right would be carbon. So it'll be one of those two, and most of you remember that, yeah, size increases left and down, so the biggest one would be sodium, all right? So again, if nothing else, if you don't remember any of the periodic trends, it's either going to be the one that's most left and down or the one that's most up and to the right. And in terms of size, it's left and down. For size of anything, the electronegativity, electron affinity, all those things are basically up and to the right, but these guys are left and down. Cool. Which one has the largest electronegativity? As I said, it's kind of the opposite of the left and down. So see if you can figure out which one that's going to be in this group. Excellent. So if you don't remember anything about electronegativity, this is another periodic trend. The most left and down here would be potassium, and the most up and to the right would be nitrogen. So it'll be one of those two if you have to guess. But anyway, almost all of you saw correctly that this one is going to be nitrogen. What's the most electronegative element? Fluorine. That's right. All right. So fluorine is the most. Things close to fluorine will be more electronegative. Which of these is not a correct Lewis dot structure? See if you can remember which one of the rules for Lewis structures and which one is not correct. Good. So when you're drawing a Lewis structure, for example, NO negative 1, we'll do that one. What you want to do is count up the valence electrons. Nitrogen is in group 5, so there's 5 valence. Oxygen is group 6, so 6 valence. You add an additional electron if it's negative, and you take away if it's positive. So this would be 12 valence electrons, or if you divide by 2, it would be 6 pairs. Usually the first atom is in the middle, but this one's so simple it doesn't really matter, so you can just put them next to each other. But like in HCN, hydrogen is never in the middle, carbon is more likely to be in the middle then. Draw a lone pair, bonding pair, that connects the 2 atoms, so that's one of my 6 pairs. I now have 5 pairs left. Outer atoms first. More electronegative, oxygen closer to fluorine, usually before the less electronegative, like nitrogen or carbon. If you look, I've got 1, 2, 3, 4 pairs. I've got 2 more pairs left. 5, 6. Now I've used up all of my electron pairs. And at the last step, then you look for octets. Oxygen has an octet. Each of these is 2 electrons, so that's 8 electrons total. That's where the octet comes from. But nitrogen only has 6. So we need to take away one of these and make a bonding pair then to connect it. Now both atoms have a octet, which means 8 electrons. And notice here how this structure, which has a negative 1, is quite different from B, all right? Answer B is actually NO plus, all right? It's not NO minus. All of these other ones are okay. They all have the octet. They have the right number of electrons around them. Any questions? Yeah.
I remember a while back you had like a rule which was like the first and second you can't have more than 4 bonds.
That's right. Yeah, totally. So like phosphorus, you can have like 5 bonds around it, but nitrogen only 4. That's right, John. Good, good, good. Other questions? Formal charges are kind of helpful to find the best resonance structure for a molecule. See if you can go through and find out what the formal charges are on that oxygen, carbon, and oxygen, respectively. There's lots of different ways to do formal charges. The official way is to take the group number of the atom, you subtract the number of lone pair electrons, LPEs, and you subtract 1/2 the bonding pair electrons, the BPEs. So for example, this oxygen on the left-hand side, or right there I guess, oxygen is in group 6, so that would be the group number. This oxygen has 1, 2, 3, 4 little dots. Each of those is a lone pair electron, so it'd be 4 or 6 minus 4. And then each of those lines is 2 electrons, so that would be 4 bonding pair electrons. You take 1/2 of that number. You could also just subtract the number of lines. That would be fine too. But either way, that oxygen then is going to have a formal charge of 0. Carbon here has 1, 2, 3, 4 lines and no lone pairs, and it's in group number 4. So 4 minus 4 means it's going to be 0. This oxygen, also group 6. This oxygen has 6 dots, 6 lone pair electrons, so we'll subtract 6, and we'll subtract 1/2 of 2, or 1. So this oxygen on the far right is actually a -1 formal charge. So it would be 0, 0, and -1. The hydrogen is 0. So if you add up all the formal charges, it has to equal the charge on the ion, if any. Any questions on that? Here's a molecule, cysteine. It's one of the amino acids. See if you can find out what the values of the angles are. So angle 1 would be an HSC, angle 2 would be OCO, and 3 here would be HNH. See if you can remember what the bond angles are going to be for those. To find the electron pair geometry, which will help you with the bond angles, you count the number of clouds around the central atom. Everybody's usually pretty good about seeing nitrogen here. Nitrogen has 1, 2, 3 bonding pairs, 3 lines, and a lone pair, which is the double dots. So 4 clouds around it's going to give it its tetrahedral electron pair geometry. And angle 3 is definitely 109 degrees. And all tetrahedrals with 4 pairs around them will be 109. This carbon, which is the central part of angle 2, this carbon has a double and 2 singles. And if you remember, and I'm not going to do it to you, but we did lots of hand sharing, and I had the hands on top of the hands, which was the double bond, the bread over the sandwich bond in the middle. So a double bond counts as like one big cloud. So if you've got 1, 2, 3 big clouds, they want to be trigonal planar geometry, and that angle will be 120 degrees. This one looks like it's 180, but the sulfur here has 2 lone pairs and 2 bonding pairs, 4 clouds total that want to be as far apart from each other. And even though it's drawn as 180, this is tetrahedral, so this is going to be 109 degrees. So A answer B here would be the right one. Remember that just because it looks like it's 180, our 2-dimensional world, it doesn't mean that in the 3-dimensional world it's actually that way. So that one's actually 109. What's the value of the bond angle when you have a linear electron pair geometry? 180, that's right. So 109 for tetrahedral, 120 for trigonal planar, and then 180 if you do have a linear geometry. An alkene is one of the organic groups we looked at, and all of the alkenes have a generic formula that's one of these up there. See if you can figure out which one of those it is. Cool. Alkenes are useful. A lot of smells and stuff have alkenes. Does an alkene have oxygen? No. This is actually the generic formula for an alcohol. Don't tell me. No, I'm just joking. Be good, man. Anyway, an alcohol has a generic formula of that, which is honestly nothing you need to know. What is this the general formula for? Yeah, alkane. Excuse me. An alkane is CnH2n plus 2, and all the alkanes from the natural gas to your gasoline in your vehicle, CnH2n plus 2. The alkenes have a double bond, so you lose 2 of the hydrogens. So the alkenes would be CnH2n. If this is an alkane and this is an alkene, anybody have an idea what that was for? Alkyne. Well done. That's right. The triple bonds and stuff have even 2 less oxygens than those. So good. So alkanes. Alkenes. Here's a gas law question. We got a sample of gas. All right. It's got a volume. It's got a pressure. It's got a temperature. What will be the new volume of the gas under those new conditions? There's a couple different ways to solve for this. See if you can figure out which of those answers it is. It's not E, unfortunately. There's no negative volume. So this is an example of the ideal gas law, PV equals nRT. And there's several ways you could solve this, all right? You could, first of all, solve for n, the moles, all right? PV over RT. You could find moles of gas into the first set of conditions and then change it to the second gas, where you're going to solve for essentially like V2. So V equals nRT over P, blah, blah, blah. However, that's a pretty long way to do it. Anytime you use R, you have to use atmospheres, liters, and Kelvin temperatures. So you'd be converting a lot of things. If you don't use R, you can get away with doing something like this, which is something we talked about in Chem 222. You set the things that are changing equal to the things that are not changing. So moles and R really aren't changing on this one. So P1 V1 over T1 equals P2 V2 over T2. A set of conditions equals the set of second conditions if you let them equal to each other. Now, if you really look at this, obviously temperature doesn't change either. But I put temperature in here because I wanted to remind you that even if you don't use R, you've got to use kelvins for temperature, all right? You never want to divide or multiply by zero. Dividing is strictly forbidden, and multiplying, of course, would cause your numbers to be chaotic. So you can really just use P1 V1 equals P2 V2 and solve for it if you'd like to, and you don't have to change anything then. If you do that, it should come out to be about 463 milliliters. And again, it's not wrong to turn to liters first and then go to milliliters. It's not wrong to go to atmospheres, et cetera, et cetera. How many millimeters of mercury in an atmosphere? 760. How many milliliters in a liter? 1,000. What do you use to convert Kelvin to Celsius? What's the magic number? 273. Good. R is 0.082057. These are the kind of things that I would definitely make sure that you know what to do. Maria.
So when using this formula, they don't have to be like ATMs or liters as long as they're the same on both sides.
That's right. Always convert Kelvin, all right, if you have temperature. But the other ones, yeah, you can get away with just using the milliliters and yeah.
What was the value of the R constant?
Someone help Emily out. This is something you should know / memorize, but you also might have this stuff. What is the number? Well done. 0.082057. So yeah, and both the gas version, Emily, and the energy versions will be things you'll see. The energy version is the 8.3145 number. Good question. Other question. Density, gas density. Which one of these will have the greatest density at about room temperature and pressure, roughly? Hint, use the other gas law. Excellent. The other gas law is what we call the evening dirt equation. So PM is like evening, this is like dirt, okay? And why this is helpful is that this D is the density of gas. So if the pressure and temperature are the same and the R value doesn't change, then the density is directly related to the molar mass of the gas. So find the molar mass of each one of those gases. Xenon is by far the heaviest of the gases, has the biggest molar mass. So xenon would be the most dense. Any questions?
If we get a problem like this, can we just look at the biggest molar mass?
That's exactly what you want to do. You bet. You bet. You bet. ideal gas law is pretty good. We spent a lot of time with it, so hopefully it's somewhat worthwhile. But there are some conditions where it's not as ideal. See if you can remember which one it is. Or does it work all the time? Not. Excuse me. Excellent. So the two times it doesn't work too well, and it works well most of the time, but it doesn't work very well under low temperature and high pressure. We talked about in Chem 222 how it looks like the volume of the gas would go to 0 at 0 Kelvin, and that doesn't make sense because an atom has volume, all right, and we're not going to make it go to zeros. So that's a problem at low temperature. The high pressure things, when the gases get close to each other, they start to experience intermolecular forces. And most of the time, intermolecular forces for gases are zero, so we basically don't talk about them. But if you start getting at really high pressures, then things begin to get weird. You can use things like the van der Waals equation, which is something we talked about in Chem 222, although we didn't calculate anything with it. The van der Waals is a good way to use these high pressure, low temperature conditions and have somewhat reputable data for gases. So it's a cool law, but it doesn't work all the time. Van der Waals is when to use it if you're at low temperature, high pressure. Cool. Questions? Good. A nearest neighbor comes from intermolecular forces of solids, all right? And you basically want to see how many atoms of the other type are around. So this is an example of sodium chloride. And I'd like you to see if you can figure out how many nearest neighbors chloride would have. How many atoms are kind of touching it, if you will. So what I would do is look at this blue one, for example, and see how many green atoms are touching it. Remember to look above and below as well. Cool. All right. Everybody picked B or C, which is really cool. The nearest neighbor is literally, you can think about it as the number of atoms that are touching the other kind. So if you focus on this blue one, all right, there's one that's going like backwards and one forwards, one to the right and one to the left. So that's where the 4 comes from. But this is a 3-dimensional object. So there's also a green one above and a green one below. So there are actually 6 of the nearest neighbors around the central one. You can think about it as from the sodium's perspective or the chlorine's perspective, it doesn't matter. We called sodium chloride-like structures octahedral in the solids lab of Chem 222. This is where the octahedral part comes from. That middle atom is surrounded by 6 of them, so it looks like it's quadrant octahedral and stuff. So, any questions? Here's a question on boiling points. Boiling points of solutions and freezing points of solutions are different than the freezing points and boiling points of pure liquids. Which one of those do you think would have the highest boiling point? So none of you thought they were the same or there wasn't enough information. So yes, well done, success. Anyway, both of these are molality. Molality is moles of solute per kilograms of solvent. And that's the little m right there. And the equation for a boiling point, delta T equals K times M times I. And K is just a constant as long as your solvent is the same, which it is, that won't change. So molality alone makes it look like B would be the best answer, all right? Because molality of 0.15 is bigger than 0.10. K is the same, so your change in boiling point looks like it would be higher. But the Van Hoff factor is what I is, and if you have an ionic compound like sodium chloride breaks up into a sodium ion and a chloride ion. So the I factor for a sodium chloride ionic compounds would be 2. Sugar is covalent, all kinds of carbons and hydrogens, no positives and negatives. The I factor would be just 1 for sugar. So 0.15 times 1 is smaller than 0.1 times 2, which is what you'd have for NaCl. So we would guess that the sodium chloride solution would have a higher boiling point. Which one of those would have the lower freezing point? So delta T equals K times M times I works both for boiling and freezing. So if you were looking for the lowest freezing point, you would also look for this M and I part as well. So the NaCl would also have the lowest freezing point. It would have the lowest freezing point and the highest boiling point. Remember to look for the I for the N for the ionic compound.
What is the K constant? What's the volume?
I don't know off the top of my head, and you don't need it for this problem, because if the solvent is the same, water, it will be the same number. So what you could do, Chloe, is you just let it equal 1, all right, or something like that. It's just, it doesn't affect what the answer comes out to. But good question. Good question. Molar mass from freezing point and boiling point can be a really good thing to know. So see if you can use this information to find what the molar mass of this compound is going to be. This is like something we did also in the freezing point section. We did the freezing point lab, although it was take home if you took Chem 222 with me because all the craziness. But anyway, blah, blah, blah. See if you can figure out what's going on. Right, I'm definitely running out of time here, so I'm going to keep going here. In this problem, delta T equals K times M times I is 1, same equation, freezing point and boiling point. Solve for molality. Molality times kilograms of solvent, 0.0500 kilograms will give you moles. And then finally, the grams divided by the moles will give you the molar mass. It comes out to be 122 grams per mole. This is a good kind of process to know for next week as well. Okay. Now the next couple examples, I'm just going to go through and talk about them. I'm not actually going to do them. So if you have your cameras and stuff, that's totally legit to get them up and running. This is a question based on kinetics, all right, where you first need to figure out the order of the A and B. And then once you know the order of A and B, you have everything. This is the rate, and these are the concentrations. You can go through and find the K. And when you do this one, it comes out to be answer D. We find out that A is first order, B is a 0 order, and then when you have that, you can go back and solve for the K. This is a kinetics problem from Chem 222. Half-life is another thing that's pretty important. You can figure out the half-life when half of the reactant concentration has been used up. So 0.020 down to 0.010 took this long, which is 654 minutes. So graphically, you just look at where the concentration goes down to half the value, and you look on the x-axis for what it would be. So this would be half of the concentration. If you have a problem where you're trying to find out how much is left or something like that, generally what you want to use is the first order integrated rate law. Natural log A over A0 equals minus KT. And sometimes the half-life expression, half-life T1/2 equals 0.693 divided by K. These will both come in really handy next week, so I'm letting you know. So in this problem, we have a half-life, say 8.04 days. 0.693 divided by that will give you the rate constant K. Then you can shove it back into this thing. The time elapsed 32.3 days. You don't know how much you have left, but you know you started with 8.8 micrograms. You can go through and solve 0.54 micrograms will be left. This is a mechanism question from Chem 222. We have a two-step mechanism, and we're trying to figure out what the catalyst is. A catalyst is something that is used up, and then it's recreated at the end. So you can see in the first step, 2 NO2s go in, but 1 NO2 comes out. NO2 is being used up, and then it's coming back in. So NO2 here would be the catalyst. An intermediate would be something that appears and disappears. So NO3 here would be something that would be an intermediate because it's appearing at the end of the slow step and beginning at the, or being used up at the beginning of the fast step. Remember that the slow step helps determine the rate law. So if this is a good mechanism, you'd have rate equals K times NO2 squared because there's 2 NO2s. There wouldn't be any CO, so CO would be 0 order. Let's do this one real fast. This is a good one. This is an example of a nuclear reaction. We need to figure out like what piece is left over. So 239 equals 0x plus 239. You want to solve for the missing part, which is 0. On the bottom, you've got 92 equals x plus 93. So when you go 92 minus 93, that equals x. There would be a negative 1 down there in the bottom. And the negative 1 on the bottom, the 0 on the top. This is an example of a beta particle. A beta particle is a fancy name for an electron with super high energy. 0 minus 1 beta would be a beta. The positron has a positive 1 down there. Gamma is pure energy. Alpha is a helium nucleus.
Oh, come where the sky and night silently flow, and the carburetors through for the oxides below, with the rays of potassium shine on the hill, and the song of the silicate never is still. Come, oh come, peroxide of soda and bivitol. Come, oh come, peroxide of soda and bivitol. While alcohol's liquid at 30 degrees, and the chemical change can affect manganese. So while alkalis flourish and acids are free, shall my true heart be faithful, sweet science to thee. Yes, to thee, yes. Zinc, borax, and bismuth, and HO+C. Yes, to thee, yes. Zinc, borax, and bismuth, and HO+C. Once sulfides and chlorides and nitrates so dear, never names to my soul can so closely go here. So while alkalis flourish and acids are free, shall my true heart be faithful, sweet science to thee. Yes, to thee. Yes.
This is me, Andrew.
Borax and bismuth and HO+C. Yes, to thee. Yes. Zinc, borax, and bismuth and HO+C.
This officially concludes Chem 223, and I want you to know what an honor it's been to have you here. I know that this is a tougher class, but you guys persisted. You're all here on the last day, which is really cool. You've hopefully learned quite a few things, and if nothing else, this review session is probably able to remember just all of the work you've done. Some of you have had since Chem 151, some of you just Chem 223. To all of you, it has been a deep honor to have you here. I have one last extra credit assignment I would like to share with you. This extra credit assignment must be submitted by email, and it has to be in my email box by Monday morning at 8 a.m. But if you were with me in Chem 221, in the syllabus, the last page was a message in a bottle, which my spring term 2018 Chem 223 class wrote to you guys in fall 2018 Chem 221. And it was just a silly list of things that people wanted you to know about, things that helped in the class, things they wish they would have known first and stuff, things they would have done differently now that they knew it. And it's time for you to write a message in a bottle to my fall 2019 Chem 221 class. So tell them what you think, some things that you wish you would have known a long time ago, some things that worked, some things that didn't work, things you learned along the way. Regardless if you're just joined me or you've been with me for a long time, all of your insights are really appreciated. They'll be totally anonymous, all right? They won't have anything limited, but it would be really fun. And if you do this by Monday morning, 8 a.m., email only, no hard copies, because copy and paste is going to be key. Extra 5 points of extra credit. Nice way to kind of finish off the term. The only thing we're doing next week is the lecture final. This morning in this room, Wednesday, 8:45 a.m., or if you're in Wednesday's group, 1:10 p.m., 2501. Have a wonderful weekend. Good luck with your finals.